So in that previous video, we looked at on Desmos the graph of a function, x squared minus 2x, and then the graph of its derivative, which we can put onto the same plane. And it's the idea that the graph of the derivative is just mapping all of the slopes of the tangent lines of that original function. So if we look at this line of our derivative, so it starts down at negative infinity, it increases up and hits 0 at x equals 1, and then it's positive. So if this line is representing slope of tangent lines, then how I could read that is on this left-hand side. So from x equals negative infinity, we're seeing negative slopes. So we have these negative slopes, and then the negative slopes get closer and closer to 0 and reach 0 at 1. And then the slopes turn positive and they get steeper and steeper, so that slope is getting bigger and bigger as x is increasing. So if we take that back to our original function, that makes a lot of sense. If we're over here on the left-hand side of our parabola, we have these steep negative slopes, and then the negative slopes are getting closer and closer to 0 until it reaches a tangent line that would be horizontal, so it would have a slope of 0 at x equals 1. And then the slopes turn positive, and then more positive, and then they get steeper and steeper and bigger positive values. So that's exactly what we're seeing with our line here of negative values until we reach a slope of 0 when we get to x equals 1, and then positive slopes where the slope is getting bigger and bigger as we increase x. So the derivative is the slope of the tangent line, and we have that the derivative is positive when the function is increasing. So if our function has this positive slope, or the slope of the tangent line is positive, then the derivative is positive. Then we have that the derivative is negative when the function is decreasing, and that is where the slope of the tangent line is negative. And our last piece is that the derivative is equal to 0 when the function is neither increasing or decreasing, which is typically a turning point, like where we're switching from increasing to decreasing. This could also come through as a local minimum or maximum value. Okay, so let's look at this graph here. So we have a graph that shows the height h of a hot air balloon over time, and we want to use the graph to sketch a graph of h prime of t. So we have our original function h of t here, and we want to sketch h prime of t. So what we can do is just looking at our graph here. So we're starting out here on the left-hand side, and what we can do is we can see we have negative slopes, and the negative slopes are getting closer and closer to 0 here. So this spot right here where I have this local minimum, this would have a slope of 0. So what I could do is I can go ahead and plot my first point for my derivative function where we would have that local minimum. We use that same x coordinate, but if I'm trying to graph the slope of the tangent line at that point, I'm graphing 0. And then what I could do is I'm going to go ahead and make a note that to the left of there we had negative slopes. So we had negative slopes, which means we'd be graphing below the x-axis. So if we graph below the x-axis, that's where our derivative is negative, or you could think of it as the slope is negative. And then if we're graphing above the x-axis, that's where our derivative is positive. So we're going to have negative values, then we're going to get to 0. And if we look at our function, we get away from 0 and our function starts to increase. So we have these positive slopes. The slopes get pretty steep here, but then they switch going back towards this slope of 0, happening at this local maximum right here. So this point as well, we know we're crossing the x-axis. And between those 2 points, we have positive slopes. So it's positive. We could make a note that it would be at about its steepest halfway between. So let's see, there's 5 units here, so about halfway between is just going to be very steep in there. So we start at 0, start to get positive, more positive, the most positive, and then the slope goes back to 0. And then we have decreasing again with, I think, our steepest slope at the end there. So decreasing, which means our slope will be negative. All right, so basically what I want to do, and I'm not going to get too technical with actually calculating the slopes, but basically we want to start from the negative region. We're going to cross at that coordinate, -2, 0. And then we know we have positive values and they reach their steepest about halfway between until it has to turn back around and hit 0 at x = 3. And then we're going to have negative slopes until we reach the end of our graph. So let's go ahead and try to sketch something like that. And we could try to estimate the instantaneous rate of change here, but I'm not too worried about it. Let's just graph something like this. Dun, 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 dun. Okay, that's good enough. So what this entails is our negative slopes, so seeing our negative rates of change, and those negative slopes get closer and closer to 0 as we reach that local minimum. Then they turn positive, so increasing away from 0. So we start having steep slopes, and then the highest positive slope is about halfway in between, where the slope starts flattening out, getting closer to 0 again. Then we have our negative slopes, and it would end there at our most negative. This is probably really extreme for that slope that's occurring there, but in terms of a sketch, this is a decent sketch of h prime of t. So our derivative function that's graphing the slopes of the tangent lines. So we stay on the same x-axis, it's just the function outputs represent something different. All right, let's relate a piece to word problems as we look into more word problems in the next section. So instantaneous rate of change, this is more terminology for the same thing. So again, in fact, let's make a list. I know I keep saying it out loud, but we have the derivative. The derivative is the same as slope of the tangent line is the same as instantaneous rate of change. And for now, what we're doing to calculate this is our difference quotient, the limit as h approaches 0 of f of x plus h minus f of x over h. All of those represent the same thing. And in terms of notation, the derivative, f prime of x. Okay, so all of these relate to each other as basically the slope of a tangent line at a single coordinate. So the instantaneous rate of change of f of x at a value a is the derivative f prime of x. So let's say we have a function that's mapping distance and time. So I'm going to let t equal time, and s is going to equal distance. So if s of t is the position of an object, so the output is mapping the distance away, t is time passing. The velocity of that function, so the velocity, if you think about like a car, that would be this measurement of miles per hour or kilometers per minute. Basically, it's how distance changes over a certain amount of time. So this is like looking at the change in s over the change in t. And with our new notation that I briefly mentioned when we talked about all of our different notation for the derivative, that notation dy dx, D is talking about this difference that's occurring. And it's kind of this infinitely small distance. It's like how we're bringing in this as h approaches 0 here. But all that to say, where I'm talking about this change in s over change in t, we could describe that as ds dt. So this is the derivative of s with respect to t. So if we want this velocity function v of t, this is going to come from the derivative of s of t. So v of t is equal to s prime of t. So if we start with this position function, we can calculate velocity from it by taking the derivative. Now, acceleration, this is talking about how velocity is changing. So how is velocity increasing or decreasing? Like in terms of driving, I think of it as putting on the gas or putting on the brakes. It's how you're accelerating, it's how you're moving forward or slowing down. So what this evaluates is how velocity changes. So is velocity increasing or decreasing with respect to time? So the change in velocity over change in time, which is the same as dv dt. So with this, we're looking at the derivative of v with respect to t. So it's like our x-axis here isn't changing, but what we're doing is evaluating the change in our y values. So if we wanted the acceleration function a of t, that would be the derivative of the velocity function. And this notation here we're going to talk about later in the term, but I'll go ahead and throw it in here, but it's kind of a domino effect here. So we're taking the derivative of the velocity function. Well, the velocity function came from the derivative of this position function, so s of t. If velocity is this one derivative of s of t, then this would be the second derivative. And how we would write that is s double prime of t. And we'll talk about this notation more, but basically we have two apostrophes there to show that it is the second derivative. Again, more on that later. Just thought we'd put it in there now. Okay, so getting into some word problem things, and eventually we'll look at graphs with these and how they relate to each other. But in terms of graphing the derivative, it's just a matter of thinking about positive and negative slopes, and then these turning points where our slope is equal to 0.